Okay, so let's start with the solution of the checkpoint from last time. This was, I think, a difficult one. So this was a question, and these were the answer choices. So for those of you who answered correctly, would anyone care to explain, to tell us what is the correct answer and why you think it is the correct answer? Okay, be brave. Not empty and not full. So what do you mean by that? Did you answer correctly the question? Okay, so you didn't answer correctly, but you said not empty and not full. What do you mean by that? So I guess you're referring to the buffer, to a buffer, but which one are you referring to? The R1 buffer. Okay, R1 buffer. So you say the one. So are you saying that the scenario which will maximize the rate of packets arriving at C is the one where R1 is not empty and not full? Okay, you can just say yes or no, if I understood correctly. Okay, all right, so, okay, so I have a comment from another student. C should be the correct answer. I got D. Oh, by the way, there's a typo here. Obviously, this should be D, right? Sorry, there's a typo here. None of these, none of these. No, the correct answer is not none of these. So I'm going to give you the correct answer and tell you why, because apparently the students who answered correctly, okay, so I have input from a student. R2 should never be empty, else it is a lost opportunity. Exactly, that is the correct answer, because you are asked about the rate of packets arriving at C. Okay, so what is sent over this link comes from the buffer at R2. Now, if there are times where the buffer at R2 is empty, then it will be lost opportunity. You're not going to maximize the rate. So if you really want to maximize the rate of the packets that arrive at C, you need to send data continuously without any idle time on the link. And in order to send the data continuously, you need to always have something in the buffer. Okay, so the correct answer is that the buffer R2 is never empty. Correct answer is B. Okay, the R1 is not directly relevant. Okay, so because you may have, for example, the buffer at R1, which is never empty, but then you may still have times where the buffer at R2 is empty because the transmission rate, let's say the transmission rate over this link is low, then compared to this transmission rate, then there will be times where the buffer at R2 is empty, right? This is not going to be fast enough to keep the buffer at R2 full. Okay, so that is essentially the key thing here. To answer correctly this question is to just focus on the buffer at R2. Any question here? Okay, If not, then let's go to the lecture. Okay, sorry, I need to fix the settings. Okay, so we have learned about RDT, which that is a mechanism to ensure that you can have reliable data transfer, right? We look at various versions, starting from RDT 1.0 and going all the way to RDT 3.0. And RDT 3.0 is the one that can handle the most realistic case of underlying channel, right? Where you may have packet loss, you may have bit errors, things like that. So that RDT 3.0 can handle, and also RDT 3.0 will work correctly. Okay, meaning that with RDT 3.0, the data will be delivered without loss, will be delivered in order, and without duplication. Okay, now let's look at another aspect of reliable data transfer, which is performance. So in order to look at the performance, I'm going to actually skip this slide for now, go straight to the next slide. And I will go back to that previous slide. Okay, so to analyze the performance of RDT 3.0, we need to remember that it is a stop and wait protocol. And stop and wait, when you do stop and wait, then the sender is going to first transmit one packet. This is what we see here, right? This is so this axis is the time axis. So let's assume that at time t0, the sender starts to transmit. So it transmits the first bit of the packet. Now this first bit, after it has transmitted the first bit, then it needs to transmit the next bit and so on, right? So it will take the transmission delay time, L divided by R, for the sender to finish the transmission. Okay, so after this amount of time, which is equal to the transmission delay, the last bit is transmitted. So the last bit is transmitted at this point in time. Now, that last bit will need some time to propagate to reach the receiver, and that is the time we see here. This is the time. Okay, so after an additional propagation delay time, the last bit is received at the receiver at this point in time. Okay, now let's assume that everything is fine. There's no packet loss. There's no bit error. Then the receiver will normally send back a positive ACK, right? After it has received the last bit of the packet, it will send an ACK. And here the ACK is a very short message. So it's a very short packet. Essentially, the transmission delay for the ACK is negligible. Okay, it's just a small number of bits. So that's essentially the transmission of the ACK doesn't take so kind of negligible transmission delay time. But there is propagation delay, right? So this is the time from here to here is the propagation delay. It's the time for the ACK to reach the sender. Now, because it is stop and wait, the sender sends one packet and then it has to stop, wait for the ACK. So during all this time, the sender is not sending anything, right? It just stops, it just waits. Wait for the ACK. So here you can see clearly that there's inefficiency because the channel, the link, or the resources, if you wish, is not utilized all the time because the sender just send one packet and then wait during all this time before it can send again. And this time is the round trip time, essentially the time it takes for this bit to go from sender to receiver, and then some short message to return back to the sender. Okay, so by definition, this is the round trip time. Okay, so after this wait time, the ACK arrives at the sender. Now the sender can send the next packet. Okay, so you see the pattern here, right? Send one packet, wait RTT, and then send the next packet, and then wait RTT. This is how RDT 3.0 operates, assuming we have no error, there's no retransmission and so on, right? Okay. So we can calculate what is the fraction of time during which the link is actually utilized. Essentially, it is this amount of time divided by this amount of time. Okay, and this amount of time, we know it is a transmission delay, so it's L over R. And this amount of time is L over R plus RTT, which is what we have here in the denominator. Okay, now this is what we're going to call the channel utilization rate. And ideally, to have maximum efficiency, we want this utilization rate to be equal to 1, right? Essentially 100%. We want to utilize the channel 100% of the time. So this is a measure we're going to use to measure the efficiency of the protocol. Okay, what is the percentage of time during which the channel is actually utilized? Okay, so let's keep this formula in mind, and now let's go back to the previous slide. Okay, so let's assume that we have a 1 gigabit per second link, so a link with a transmission rate of 1 gigabits per second. Let's assume we have a 15 millisecond propagation delay on that connection between the sender and the receiver, and we have a packet which is 8,000 bits. So we can calculate the transmission delay, just use this formula, right? So 8,000 bits divided by the 1 gigabits per second, we get 8 microseconds. Okay, now, so L over R is 8 microseconds, and then round trip time is double the propagation delay, right? So it's 30 milliseconds. So we plug in the numbers into this formula that we have derived previously. We get this value. This is the channel utilization rate when we use RDT 3.0 under these assumptions. And these assumptions are actually very reasonable. Okay, so these numbers are very, very reasonable numbers. And we can see that this is ridiculously low. Okay, so it is what? It's 0.027% of the time we're using the channel. Very low. Okay. So if we use the channel this percent of the time, we can calculate on average what is the throughput. Okay, on average, how many bits per second do we transfer, given that we have this idle period. So if we do the math, then we just transmit 1 kilobyte packet, right? Kilobyte packet every 30 milliseconds. Okay, so every round trip time we transmit one packet. Okay, and the packet is 8 kilobytes. So the throughput is 33 kilobyte per second. 33 kilobyte per second actual throughput on average, but the link is 1 gigabits per second. Okay, so we are very far from utilizing the whole resources. So here we have a good example of a protocol, RDT 3.0, which limits the efficiency or limits the use of the physical resources, right? Because here in theory, we could transmit up to 1 gigabits per second. Okay, so we have gone through the analysis. On the next slide, why the utilization is so low. Essentially because we do stop and wait. Any question? Okay, so now how can we improve the channel utilization? Okay, this is very low. We need to do something about this. So in order to improve the channel utilization, we are going to use what is called pipeline protocols. So the idea of pipelining is that instead of sending only one packet and then wait for the ACK before sending the next packet, the sender is going to send multiple packets. Okay, so it's going to send multiple packets, and then it's going to wait for the ACK. And then it will send, after that, it will send another batch of multiple packets, and so on. Okay, so that is what is called pipeline protocols. So send multiple in-flight yet to be acknowledged packets. So now the issue here, remember we had that discussion on Piazza, for those of you who read Piazza, who logged on to Piazza, about, okay, so how can you identify unambiguously, right, the acts. So now the problem, so we saw that with a 1 bit of the sequence number, we have no problem. There's no ambiguity, right? So RDT 3.0 works fine, no ambiguity. But now, if we send, let's say, 4 packets, let's assume we send 4 packets before we wait for the ACK. But if we only have 1 bit for the sequence number, then if I look at the sequence number of my 4 packets, I'm going to have one packet which is sequence 0, another one will be sequence which is 1, another one which is 0 again, right? Because I have only 1 bit, and I want to encode actually sequence number 2, but because I have only 1 bit, so it's 0, and then another packet which is 1. Okay, so I send sequence 0, 1, and then 0, 1. But actually, these are 4 different packets, right? So there's a problem here because if I receive the ACK and if I receive ACK of 0, I will not know what packet is being ACKed because I sent 2 different packets with sequence number 0. So when we do pipelining, we need to have more bits for the sequence numbers. Okay, we need to increase the range of the sequence number to avoid ambiguous ACK. And then another thing that will be needed is that we need to buffer at the sender, and also depending on the actual pipeline protocols, we may also need to buffer at the receiver. So we'll see later why we need to buffer the receiver, but at the sender, remember, we need to retransmit if there's a loss, right? So as long as the packet that has been sent has not been positively ACKed, we need to keep a copy of it. The sender needs to keep a copy of it so that it can be retransmitted if needed. So that requires buffering at the sender. So here we have an example of a case where this is useful to do pipeline protocols. So here we have a large round trip time because it is a long distance between the West Coast and the East Coast. And if you just use a stop and wait, like RDT 3.0, you're going to send only one packet. You have to wait for that packet to do the whole round trip time, right? Packet and then the ACK before you send the next packet. But if we do pipeline, we are going to send multiple packets, and then we'll have multiple ACKs, okay? So no more stop and wait. And the pipeline protocols, they are also referred to as sliding window protocols. And we'll see next shortly what does that mean exactly. Okay, now we are going to do pipelining. And in order to do pipelining, the sender, we need to keep a list of all the packets that it is allowed to send. And that list is going to be kept in a sending window. It's called the sending window or sender window, okay? The receiver will also maintain a list of the acceptable sequence numbers. And that will be called the receiving window. And during the protocol, the operation of a sliding window protocol, the window will appear to be sliding across the packet. Okay, so we'll see shortly some examples. And that is why it is called sliding window protocol. And also another thing is the sender and the receiver, they must have compatible windows. And this is, for example, it could be negotiated at the setup phase, right? During connection establishment phase, negotiate the windows so that the sender and the receiver, they have compatible windows. So again, all of this will become more clear as we look at examples. Okay, let's go straight to an example. Okay, so here to explain the concept, I am going to assume that we have enough bits for the sequence number so that these are the sequence number of the packet. So I do not have 0, 1, 0, 1 anymore, right? But I have 0, 1, 2, 3, and so on. So in this case, I have at least 4. So because I can encode up to 8, so I have at least 4 bits for the sequence number. Okay, so initially at the sender, here I assume that the sending window has a size 3. So that means the sender is allowed to send 3 packets before it has to stop and wait for the ACK. And these are the 3 packets that the sender is allowed to send. These are the sequence numbers of these 3 packets, 0, 1, 2. Okay, so let's assume that the sender sends the first packet. It uses sequence number 0, that first packet. B receives the packet. Remember, we no longer stop and wait, so the sender can send right away another packet without waiting for the ACK for this one. So here it sends the packet with sequence number 1. The content is B. They are both received at the receiver. And the sender sends the third packet with sequence number 2. Okay, so it has used up the window. Okay, so now the receiver acts the packets. So it has received the packet sequence number 0. So it sends back ACK of 0. So here I just changed slightly the notation. It's called OK instead of ACK, right? So, but essentially that means ACK of 0. It has received packet sequence number 1, so he sends back ACK of 1. Okay. Now, let's look at the sender side. The sender side, after it has sent 3 packets, it has exhausted the window. It has used all the sequence numbers in the window. So now it has to stop and wait for the ACK. It's not allowed to send any more packets before it receives the ACKs. And also here in the slide, the numbers, the sequence numbers which are not yet used to send a packet are shown in green, and the ones which have been used to send the packet are shown in red in italics. Okay, so 0 is used, 0 and 1 have been used, 0, 1, and 2 have been used. So sender has to wait for the ACK. Now, it receives the ACK of 0. So essentially, as far as the sender is concerned, we are done with packet 0. It has been sent, it has been received, the sender has received the ACK. We no longer need to worry about packet number 0. So now the sender will slide the window to the right, and now because it slides the window, so the sequence number 3 is now inside the window. Okay, and therefore the sender is allowed to send a new packet with sequence number 3. But let's assume that it does not yet have data, right? It has no need to send anything, so the window stays in this state. And now the sender receives the ACK of 1. So once again, it's going to slide the window because we are done with packet number 1. Slide the window, and now there are 2 sequence numbers, new sequence numbers, which are usable by the sender should it want to send new packets. These new sequence numbers are 3 and 4, because now 3 and 4 are inside the sending window, okay, because they slided the window. So now 3 and 4 are in the window. So assume that after that, the sender has data to send, right? So it's going to use the first green sequence number in the window, which in this case is 3. 3 to send this packet, this new packet. Okay, it's not going to use the one which are red because they have been used already, and they're waiting for the ACK, right? So 1 and 2 have been sent, but waiting for an ACK. And then here it receives ACK of 1, so we no longer wait for an ACK of 1. We can slide the window, but the sender is still waiting for an ACK of 2. ACK of 2. So still waiting, and so 2 is still in the window, but it is red. Okay, finally, the ACK of 2 arrives, and the sender will slide the window again, and this is going to be the new window after the ACK of 2 has been received. Okay, so at any given time, with the receiving window, the sending window, the sender is constrained. Is not allowed to have more than, in this example, 3 packets outstanding. Outstanding meaning the packet has been transmitted and we are still waiting for an ACK. Yes, the window only slides when an OK is received. When an OK is received at the sender. Okay, not sent, but received. Okay, and then I have another question. If receiver receives packet out of order, does the window still slide? Okay, so that is a very good question, and I will simply ask you to just wait a little bit, and we will look at these issues. Okay, and then the sender will, let's assume we have one more packet to send, so we'll use the first green green one, the first green sequence number, which is 4, to send the packet. Okay, so now if we have a window size of 3 packets, we can go back and then recalculate what is the channel utilization when we do pipelining with a window size of 3. So essentially it's the same analysis as before, that we have a transmission delay for the first packet. We have another transmission delay for the second packet, and a third transmission delay for the third packet. Okay, so the only difference is here we send 3 packets instead of 1, and we have the ACK for the first packet that comes back. We will have the ACK of the second packet that comes back, and so on. But essentially, after round trip time, the sender is able to send 3 more packets, right? So send 3 packets, wait for the ACK. When it receives the ACK, it sends 3 more packets. And if we do the same analysis as before, then we can calculate the channel utilization rate. And now we see that this is the time during which the channel is utilized. So it is 3 times L over R. And this is the denominator, right? So over this interval, time interval, which is L over R plus RPT, we utilize the channel this much time. So it's essentially, we compare to the previous case of stop and wait, RDT, we have triple the utilization rate, multiplied by 3. And this is what we get, essentially because we send 3 packets instead of 1. Any question? Okay, so now, up to now, everything seems to be fine. We can improve the utilization rate, but we need to think about the cases of packet loss and things like that, right? Retransmission. So let's look at this example just to show you what is the issue here. So if we want to do reliable data transfer with pipeline protocol, we may have this scenario. Here, I assume that the window size is 4. Okay, so this is what I have in the sender window. And the sender can send 4 packets because the window size is 4. But now, let's assume that this packet is lost. Okay, so the receiver receives packet 0, receive packet 1, does not receive packet 2, receive packet 3. Okay, now remember, reliable data transfer means that the data at the receiver should be delivered to the upper layer without loss, right? Without any loss. So in this case, we have a loss of packet 2. There's a gap here. So this packet 3 cannot be delivered to the upper layer. 0 and 1 can be delivered. They are in sequence. There's no gap. But packet 3 cannot be delivered because packet 2 is missing. There's a gap. So now there are some kind of conceptual issues or questions that we need to ask here. Is that first question, if the receiver receives packet 3 with a gap, should it save or should it discard packet 3? Okay, given that packet 3 cannot be delivered right away to the upper layer. So should it save packet 3 for later delivery or should it discard it? Okay, that's the first question. And then the second question is, in that case, what feedback should be sent? Okay, what feedback should be sent? So these are the answers. The receiver could, so depending how we want to design the protocol, we could choose a design where the receiver save or where the receiver discards. It's really a design choice. Okay. So now I think you can imagine easily that if the receiver saves a packet, it's going to be more complex implementation, right? The receiver can save the packet so that later when it receives packet 2, eventually, it will be able to deliver packet 2 and then packet 3. But that will make the receiver more complex, right? Now we could choose to make it simple by just saying, okay, so packet 3 is out of order. I just discard packet 3, knowing that at a later point in time, packet 3 will have to be retransmitted. Okay, so it's a design choice. And then the answer to question 2 is that if the receiver chooses to discard packet 3, it should not send ARC of 3, right? Because essentially ARC of 3 would mean that everything has been received up to packet 3. So that, I mean, these kind of 2 questions, they are kind of related, right? Okay. So keep that in mind. There are 2 possible design choices. One is to save the out of order packets. The other one is to discard. Okay, so given that, then we end up with 2 basic approaches. One is called go back N, the other one is selective repeat. So in go back N, use simplicity, which means the receiver will discard the packet 3 in the previous example. Okay, so any packet that is received out of order or with a gap will be discarded. The advantage is we're going to have a simple implementation, but the disadvantage is that if we discard packet 3, we know that later, eventually packet 3 will have to be retransmitted. So it is less efficient utilization of resources, right? Essentially, the first time packet 3 was received correctly was not lost, but still the sender will have to retransmit packet 3. So there's a loss in throughput when, there's a kind of penalty, right? Penalty in throughput when there are losses that, okay, if we lose packet 2, then we also lose packet 3, even though packet 3 is not actually lost, but we lose packet 3 in the sense that it will have to be retransmitted. Okay, the other approach is when we save packet 3. Okay, so that approach is called selective repeat. It's going to be more difficult, more complex from an implementation viewpoint, but we will have a better efficiency because packet 3 will not have to be transmitted. Any question? Okay, so by the way, go back and selective repeat, they're also this kind of conceptual protocols, if you wish. And what I mean by that is that on the internet, we do not have a protocol called go back and we do not have a protocol called selective repeat. But they are very good at learning the concepts. Okay, so these are 2 protocols which are taught in every computer network class. Okay, so now let's look at the overview of go back and also selective repeat. So both go back and selective repeat are pipeline or sliding window protocols, which means there's a sending window of size n, or n is a parameter, right? It's a parameter of the protocol. And with the sliding window of size n, the sender is allowed up to n packets in the pipeline which are unacknowledged. With go back n, the receiver will only send cumulative ACK, which means it's not going to acknowledge a packet if there is a gap. So in the previous example, the receiver will not send an ACK of packet 3 because packet 2 is missing, right? So even though it receive packet 3, it's not going to send ACK of 3. Okay, instead, what it's going to send will be ACK of 1 because it has received all the packets up to packet 1 without any gap. Okay, and that is what is meant by cumulative ACK. And also, remember, we need to deal with packet loss. We need to have a timer for retransmission. Remember RDT.0? So here also we need to have a timer because we may have packet loss, right? Loss or the ACK being lost. So the sender cannot wait forever for ACK. We're going to have a timer. In the case of go back N, the sender will have one timer, a single timer, only one timer for the oldest unacknowledged packet. So when the packet is sent, it will start a timer, but there's only one timer which is running for the oldest unacknowledged packet. And when the timer expires, so here pay attention, when that timer expires, it will retransmit all the packets which are unacknowledged. All the ones which are still waiting for an ACK will be retransmitted. Okay, so we don't know if these packets have been lost or not lost. Simply, when this timer expires, just retransmit every packet that has been transmitted but still waiting for an ACK. Okay, so this is another source of inefficiency with go back N because most likely the sum of this retransmission will be unnecessary, right? Because these packets, they will probably be received, but just need to wait for the ACK. Here we don't wait, we just retransmit. Okay, I have a question from a student. N is the number of pipelines or packets. N is the size of the window. So it's the number of packets. And by the way, here when we say pipeline protocol, it's just a name, right? We're not referring to any specific pipeline. There's only one pipeline between the sender and the receiver. Okay, so capital N is the number of packets that the sender is allowed to send before it has to stop and wait for the ACK. Okay, now let's look at selective repeat. So selective repeat is also a sliding window. So the sender, same thing, right? It can have up to N unacknowledged packets in pipeline. But now this is the difference between go back N and selective repeat. The receiver will individually ACK every packet. Okay, so individual ACK instead of cumulative ACK. So to take the example of before, where we lost packet number 2 and we received packet 3, if we run selective repeat, the receiver will, when it receives packet 3, it will send back ACK of 3. Okay, so ACK of 3 simply means that packet 3 has been received. It does not imply that it has been received without any gap. So the sender knows that it does not need to retransmit packet 3. Packet 3 has been received. And the sender, in the case of selective repeat, will maintain a timer for each unacknowledged packet. So every time it sends a packet, it will start a timer. So, and that timer will be deactivated when it receives the ACK. Now, if it does not receive the ACK before the timer expires, it will retransmit, but retransmit only that packet. Okay, so associated with each packet, there is a timer. Okay, so I think one way you can look at selective repeat is that selective repeat is is like a multiple concurrent RDT 3.0 for each packet. Okay, so it's like you're running RDT 3.0 n times. You can have up to n RDT 3.0 processes running concurrently, one for each of the packet in the sending window. Any question on go back N and selective repeat? Okay, now let's look in more detail at the sender for go back N. So remember, if we do pipeline or sliding window, we need to extend the range of sequence numbers. So we're going to have k bits for the sequence number. Instead of 1 bit, we're going to have k bits. So k is also a parameter, right? How much of the range we want to have, that will set the value of k bits. And this is the window at the sender. So window size n, and each of these vertical bars is a sequence number. Okay, you can think of each vertical bar as a sequence number. Okay, we have inside the window, we have some sequence numbers which have already been used to transmit a packet, but the packet has not yet been ACKed, and these are shown in yellow. Okay, so they are sent, but not yet ACKed. We're still waiting for the ACK. And then we have some sequence numbers which have not been used yet to send a packet, and they are shown in blue. Okay, so they are usable if needed, but they are not yet been used. So at the sender side, so this is the window at the sender side. At the sender side, there are two state variables. One is called send base, and send base is the sequence number, the lowest sequence number in the window. So it's this sequence number. And then we have another variable, which is called next sequence number. And that one will be the sequence number of the first sequence number that is usable, not yet sent. Okay, so if the sender is in this state, and if it has a new packet to send, it will use a sequence number for that new packet, next sequence number. It will use this one. And then it will shift. So next sequence number will now shift to the right to be the next one. Okay. And the one in white are not usable because they are outside of the window. So this is by definition of sliding window. The sender is not allowed to transmit more than what the number of packets in the window before it says to wait for the ACK, right? So it's not allowed to use these sequence numbers. And then the one on the left of the window, they are shown in green, and they're the ones that are already ACKed. So we are done with, right? This is the past. We don't need to worry about these packets, the packet with these sequence numbers. They have been processed. They have been received at the receiver. They have been ACKed. Okay, now the sender is going to receive ACKs from the receiver. And remember, in go back N, the ACKs are cumulative ACKs. So that means if the sender receives, let's say, ACK of 5, that means it has received all the packets up to and including packet number 5 without any gap. Okay, that is the meaning of cumulative ACK. Also, the sender may receive duplicate ACKs. So, for example, it may receive ACK of 5 and then ACK of 5 again. And we'll see later why that may happen. Okay, I said earlier, the sender maintains only one timer for the oldest in-flight packet which in this case is this one, the packet with this sequence number. This is the oldest one, waiting for an ACK. So there's a timer associated with this one. And when the timer expires, okay, actually so when the timer expires, the sender will retransmit all the yellow packets. All these yellow, all the ones that are waiting for an ACK will be retransmitted. Okay, now let's look at the FSM for the sender. Actually, let's take a checkpoint now, and it's going to be, what checkpoint is that? Okay, bear with me. I think it's 5-1, but let me check. Actually, we're going to have 2 checkpoints today. Okay, so okay, 5-1, yeah, correct. 5-1. Okay, this is a password for checkpoint 5-1. And then later we will do another checkpoint, which will be 6-1. I'm sure that as you get more practice, you will score better in the checkpoints. Okay, let's look at the FSM for the sender in the case of go back N. So the sender is in this state where it waits for data to be sent, right? That needs to be sent. And this is the initialization step. So it needs to initialize the window, the sending window, which means it needs to initialize 2 variables. One is the send base, and the other one, which is next sequence number. Okay, so we assume here that we start with sequence number 1. Sequence number 1, okay? Base 1, next sequence number 1. Okay, initialization of the sending window. Okay, the first thing that may happen is there's data to be sent. Okay, data to be sent. So now the first thing the sender needs to do is to check that it is allowed to send, right? That the window is not exhausted. So this is how it can check. It checks that the next sequence number is within the window. Okay, base plus n. Base plus n is the if the next sequence number is less than base plus n, that means that next sequence number is inside the window. So it can use next sequence number as a sequence number for this packet. Okay, so if that is true, then it's going to build a packet, make a packet, use next sequence number as a sequence number for the packet. This is the data, and attach a checksum. Okay, so it makes the packet, and then this will be the send. So it will send the packet, with that next sequence number. Okay, send it over the unreliable channel. And now it needs to do one more thing, which is to check whether this packet is going to be the oldest unacknowledged packet. In other words, if there's no other pending unacknowledged packet in the window. If so, then it needs to start the timer. Okay, so the test is if the base is equal to the next sequence number. If the base is equal to the next sequence number, that means that there was no yellow. You watch, there was no yellow packet in the sending window, and this packet will be the first yellow packet, right? The first one in the window. So needs to start a timer that will be associated with this packet, and then increment the next sequence number. Okay, so this is what happens if there is still a sequence number available in the window. Else, if the window is full, then simply refuse the data. Okay, it's not able to send. You need to wait for to have some available sequence number in the window. Okay, now it has to, once it has sent, let's assume it has sent this packet. Now it's going to wait for the feedback. Okay, so the first type of feedback is that it receives the packet, a feedback, and it is not corrupted. So it's going to update the base. So this means sliding the window. Okay, sliding the window to update the base to be the acknowledgement number +1. So let's take a concrete example. At the beginning, it sent packet number 1, right? Sequence number 1. It received an ACK of 1. Okay, get ACK number, receive packet, and this is 1. So it's going to be 1 + 1, so it's going to be 2. It updates the base to be 2. So now the window starts at 2. It has slided the window. Okay, and then it needs to check whether this base, whether the packet has been acknowledged, that has just been acknowledged, is the oldest unacknowledged packet. So to check that, you're going to check that the base is equal to the next sequence number. Okay, so the base, let's say if it is 2, right, and this is next sequence number is also 2, that means that now there is no more yellow packet. There was one that yellow packet has been acknowledged, the yellow packet. There's no more yellow packet in the window, so should stop the timer. There's no unacknowledged packet, so there should be no timer. Stop the timer. If not, then it should start the timer, because now the packet 1 has been acknowledged, and packet 1 is no longer the oldest unacknowledged packet. Now it's packet 2. So it's going to start the timer for packet 2. Okay. Okay, another type of event is the timer times out. So it's going to, in that case, it's going to restart the timer, and then it's going to retransmit all the packets, all the yellow packets in the window, which are the one here, okay? So starting from base, going all the way up to next sequence number -1. So all these sequence numbers are the one which correspond to packets are waiting for the ACK, and they're going to be retransmitted when the timer times out. Okay, now if the sender receives feedback and it is corrupted, it will simply ignore, do nothing, because this is garbage. So just ignore it, do nothing about it. Okay, now let's look at the receiver, the FSM for the receiver for go back N. The initialization step. So here the receiver will maintain also a window, but remember the receiving window is the range of sequence number which are accepted by the receiver. In the case of go back N, the range is only one sequence number. It's always going to be the next expected next sequence number, right? So initially it starts with expect to receive packet number 1. After it receives packet 1, it's going to increment and expects to receive number 2. Now, if it receives number 3 with a gap, no, it doesn't receive 2 but receive 3, it will discard 3, remember, and still wait for 2, right? Because 2 is 1. So we'll wait for 2. It will wait for 2 until it receives 2, at which point it will update the expected sequence number to be 3, and so on. Okay, so the range of sequence numbers accepted by the receiver is only one number, which is the expected next sequence number. Okay, so that is a state variable at the receiver, which is initialized to be 1. And here the receiver will build a packet with the expected sequence number ACK of 1 with a checksum, and just builds it, right? Just build it, just have it ready. And then it goes into this wait state. So essentially here we have two types of events. So first type is the receiver receives a packet that is not corrupted, and it has the matching sequence number. So the sequence number matches the expected sequence number. So everything is fine, right? Everything is in order. There's no gap. The receiver will extract the data, will deliver the data to the upper layer. Data is delivered without loss, without misordering. And it's going to build the ACK. So it's going to ACK. The sequence number carried by the ACK will be the expected sequence number, because that is what it has received. Okay, expected sequence number, ACK, has a checksum to protect the ACK, because the sender needs to detect if there's an error, if the ACK is corrupted, and then send the packet, and now increment the expected sequence number. Okay, so it has received the packet number 2. Now the next expected sequence number is going to be 3. And any packet that it receives that is not 3 will be discarded. And that is what we have here. Okay, default means that any case that is different, whether either the data is corrupted or the sequence number does not match the expected sequence number, it will simply send back the ACK that was built previously, right? So, for example, if it has received sequence number 1, it sends ACK of 1 here. But then let's say that after that it receives packet number 4. So there's a gap, right? Packet 1 and then packet 4. It will send again ACK of 1. So it send this is the ACK that was built here, ACK of 1. It sends ACK of 1 because it is a cumulative ACK. ACK of 1 means everything has been received without a gap up to packet 1. Okay, so it discards, it does not do anything, it does not extract the data, just discard it, but still it needs to send an ACK. So here we can see that we have duplicate ACKs, right? Because if the receiver receives packet number 1, it sends ACK of 1, and then if it receives packet number 3, okay, without receiving packet number 2, it will send again ACK of 1. So we have duplicate ACK. And then at the receiver, it's pretty simple because it only needs to have this variable, which is the expected sequence number. You need only to remember expected sequence number. So the receiving window for go back n is of size 1. You only have one number in the receiving window, which is the expected sequence number. Okay, so I said earlier, if the packet is out of order, meaning if there's a gap, discard it, do not buffer, do not try to save the packet, and then send back again the ACK of the highest in order sequence number. In this example, it was sent back ACK of 1, right? Okay, I think we can let's take a break. Oh, okay, I'm trying to answer this question. I'm confused with the dash arrow. The next event is to its right or left. Next event, this is what happens at the beginning of the process. This is the initialization steps that take place. And then we go into this state. That answer your question? What do you mean by next event? Yes, just look at the slide for the sender side. Initialization, that's what we do as initialization. Okay, let's take a 5-minute break. We need to catch up. So we'll be back at 1:42. And I'm going to stop the recording.